Lesson 7.2 Code Documentation Generator. Project Overview. Here's the problem we're solving. Imagine inheriting 500,000 lines of legacy code with almost no documentation. Every new developer who joins the team needs weeks just to orient themselves. Every bug fix turns into an archaeological dig. This project builds an AI-powered documentation generator, one that produces high-quality doc strings, README files, and API documentation directly from source code. We're talking about compressing months of manual documentation work into weeks and doing it consistently. This is a 90-minute advanced project, and by the end of it, you'll have something genuinely deployable. Project goals. The business case here is concrete. Documenting 100,000 lines of code manually takes a team of engineers months. This system does it in weeks. Companies typically see a 60% improvement in code maintainability and a 40% reduction in onboarding time for new developers. The cost savings alone, somewhere between $50,000 and $200,000 annually, make this the kind of project that gets engineering leadership's attention fast. On the technical side, we're targeting a doc string quality rating above 4 out of 5 from real developers, documentation coverage above 95% of all functions, and generation speed under 1 second per function. And critically, this isn't Python only. The system will handle Python, JavaScript, Java, and more. Multi-language support is what separates a useful tool from a great one. Phase 1. Problem definition. One bakes a cigar. There are 3 distinct output types this system needs to generate. The first is docstrings, inline documentation attached directly to functions and classes. Here's what that looks like in practice. This is the core pattern our model needs to learn. On the input side, a function called calculate_discount that takes price and discount_% and returns a rounded float. No documentation whatsoever. On the output side, a complete Google-style docstring that explains the function's purpose, documents each argument with its type and meaning, describes the return value, specifies that a value error gets raised for invalid discount percentages, and even includes a usage example. That last part, the example, is what separates documentation that's technically complete from documentation that's actually useful. When a developer hits this function at 11 p.m. debugging a pricing bug, that example is what saves them. The second output type is README files. This markdown template shows the structure our model targets: a project title, a concise description, installation steps, usage examples with real code, and an API reference section. The key insight here is that README quality directly determines whether an open source project gets adopted or ignored. A model that can generate this structure from a code base and populate it with accurate content is genuinely valuable. Notice the hierarchy. Description first, then how to install it, then how to use it, then the deep reference. That ordering mirrors how a developer actually approaches an unfamiliar project. The third output type is inline code documentation, comments that explain algorithmic logic. This snippet shows a threshold-based filtering loop. It iterates from 0 to n, checks whether each element exceeds a threshold, and if so, appends double that element to the result. The documentation challenge here is different from docstrings. You're not describing an interface, you're explaining intent. Why is the element doubled? What does the threshold represent? Good inline comments answer the why, not just the what. That's the nuance our model needs to capture. Phase 2. Data collection. The training data comes from the stack, one of the largest code datasets available, containing permissively licensed source code across dozens of languages. This loading script uses load_dataset with streaming =true which is critical here. The stack is enormous, and streaming lets us process it without loading the entire thing into memory at once. We iterate through examples and filter for any code containing triple-quoted strings, our proxy signal for the presence of docstrings. Every 1,000 examples, the script prints progress so you can see the filtering working in real time. What you're looking for in the output is a healthy ratio. If you're seeing documented examples in roughly 10 to 30% of files, the filter is working correctly. The final count tells you how large your candidate pool is before the next extraction step. Raw files containing docstrings aren't training data yet. We need to extract structured pairs of code and documentation. This script uses Python's AST module to parse each file into an abstract syntax tree, then walks that tree looking for function def and class def nodes. For each one, it checks whether a docstring exists and whether it's meaningful. The 20-character minimum filters out placeholder comments like Shaq to Teddy that slip through. The remove docstring function then strips the docstring from the code using regex, giving us the clean input. The pair is undocumented code in, correct docstring out. That's the supervised signal the model trains on. Results get written to a JSON lines file, one pair per line, which is the format we'll feed directly into the training pipeline. Format_for_training is where raw pairs become model-ready examples. The function wraps each code snippet in a chat-style message format with 3 components: a system prompt that instructs the model to generate Google-style docstrings, a user message containing the undocumented code, and an assistant message containing the correct docstring. This structure matters because it teaches the model not just what good documentation looks like, but how to behave when asked to produce it. After formatting, the data splits 80/20ths into training and validation sets. The validation set is your honest signal during training. It tells you whether the model is learning to generalize or just memorizing examples. Both sets get written to separate JSON lines files, and the printed counts confirm the split happened correctly. Phase 3, Model Training. The training configuration follows the same structure as lesson 7.1, but with 3 deliberate differences tuned for code documentation. First, max_seek_length is set to 4096. Code functions can be long, and truncating the mid-body would corrupt the training signal. Second, temperature is set to 0.5 during inference, slightly higher than you'd use for factual tasks, because good documentation requires some creative synthesis, not just pattern matching. Third, num_train_epochs is set to 5. Code structure has more syntactic complexity than conversational text, and the model benefits from additional passes to internalize language-specific patterns. Phase 4, Evaluation. Evaluating documentation quality automatically is genuinely hard, but this scoring function gives us a principled approximation. It checks 5 criteria: minimum length above 20 characters, whether function parameters are mentioned by name, whether return value semantics are addressed, whether the documentation is substantive rather than a one-liner, and whether a usage example is present. Each criterion contributes 1 point, with the example check adding a bonus point capped at a total score of 5. The reason this rubric works is that it mirrors what developers actually care about. A docstring that names the parameters but never explains what they mean scores lower than one that does both. Run this against your validation set after training, and you'll have a concrete quality signal, not just loss curves. Phase 5, IDE Integration. Yes, this is where the fine-tuned model becomes a tool developers actually use. The VS Code extension registers a command called write extension.generate docs write. When triggered, it grabs either the selected text or the current function. then makes an HTTP post request to a local inference server running on port 8000. The same model you just trained, now served as an API. If the response comes back successfully, the extension inserts the generated documentation directly above the selected code in the editor. No copy pasting, no context switching. The developer highlights a function, hits the keyboard shortcut, and the doc string appears. If the API call fails, the extension surfaces an error message rather than silently doing nothing, which is exactly the right behavior for a developer tool. Project complete. You've built and deployed a code documentation generator from data collection through model training, quality evaluation, and IDE integration. Coming up in lesson 7.3, Legal Document Analyzer. Here's the full documentation generation pipeline as a data flow. Source code, Python, TypeScript, Go, whatever language, enters an AST parser, which decomposes it into function and class chunks. From those chunks, the system extracts function signatures and type hints, the structured metadata that tells the model exactly what it's documenting. That structured input feeds into the DocGen LLM, which produces doc strings and markdown documentation as output. The reason this pipeline works better than feeding raw source files directly to the model is precision. By extracting signatures and type hints first, you give the model exactly the signal it needs, parameter names, types, return annotations, without forcing it to reparse the entire file on every inference call. Here's a concrete before and after. The input is a function that calculates intersection of a union between two bounding boxes, a common metric in computer vision. The function body is pure math, coordinate arithmetic, area calculations, intersection logic, no documentation. The output is a complete docstring. What the function computes, the 4 float arguments representing box coordinates, the float return value between 0 and 1, and a working usage example. Notice that the generated docstring doesn't just restate the code, it explains the semantic meaning, intersection over union as a concept, what the coordinate format means, what the return range implies. That's the difference between documentation that describes and documentation that teaches. This diagram shows how the documentation generator scales to an entire code base. It starts with your Git repository. A code scanner traverses every function and class, building a complete inventory. That inventory feeds into the DocGen LLM in batch, not one function at a time, but processed efficiently across the whole code base. The generated documentation is then merged back into the source files, keeping docs co-located with code rather than in a separate system. From there, mkdocs or Sphinx picks up the documented source and builds a polished documentation site. The end result is a published API doc site that stays synchronized with your code. The critical design decision here is the merge step. Documentation that lives alongside the code gets updated when the code changes. Documentation that lives elsewhere gets stale. This quality comparison chart shows human-written documentation versus LLM-generated documentation across 6 metrics: completeness, accuracy, code examples, parameter coverage, return documentation, and raises documentation. Human-written docs score higher overall. That's expected, and it's honest. The contextual understanding a senior engineer brings to documentation is real. What's interesting is where the LLM scores are competitive. Parameter coverage and code examples are close. Those are the structured, pattern-driven aspects of documentation, exactly where a fine-tuned model excels. The gap is largest in completeness and accuracy, which reflects the model's occasional failure to capture domain-specific nuance. The practical takeaway: use the model to generate a thorough first draft, then have a developer review for accuracy and completeness. That workflow captures most of the time savings while preserving the quality ceiling that matters.